Our next speaker is Dr. Harold Brooks. He's a senior research scientist at the National Severe Storms Lab, NSSL, here in Norman, Oklahoma. He has an undergraduate degree from William Jewell College with a year at the University of Cambridge. He has an MA, and I guess that's a Master's of Philosophy, from Columbia University, and a PhD from the University of Illinois in Atmospheric Sciences. And after graduating from Illinois, he was a postdoc at NSSL and joined the permanent staff here in 1992. Dr. Brooks has been very active and given presentations in 28 U.S. states and 12 foreign countries. He's extensively published and has received numerous awards, and we are very fortunate that he is among us, and we are very pleased that he is here today to talk to you about regional weather variability and weather forecasting. So with that, Dr. Brooks.
When Jerry asked me to do this, this sounded like a really good idea. And then I started thinking, boy, I've got two different topics, and I'm not completely sure how this is gonna work. And we'll just see. We will all find out together how well this works as this goes along. Okay, so I want to focus on what I think are some big questions, that particularly that may be relevant to us, and that's the how and why are weather hazards distributed the way they are. We live in an area of the country and that on the planet where we get a wide variety of things happening, and I'm not going to touch on all of the weather hazards, but enough of them hopefully to give you a feeling for what the issues are, and how do we try to forecast them. What takes place into that process? We'll do a little bit of talking about that, and then the big question that I think in a lot of ways we go through is: are things changing in time, and will they? What do we know about what's happened with the past record, and what do we expect to happen in the future? And those are difficult challenges. I'm going to start by looking at severe thunderstorms. And in the United States, there's a technical definition for a severe thunderstorm. It's either got a tornado, it's got winds of at least 50 knots, or causes wind damage, and hail of at least 1 inch. So if you hear the phrase severe thunderstorm, that's what that means. And those are derived. Many people aren't aware of this. The wind and the hail threats are essentially derived from what caused damage to an Air Force training aircraft in the early 1950s. That was how we came up with those definitions. And of course, once we define something, it cannot be changed. And so that's what we actually did change hail from 3/4 of an inch to 1 inch. That was a really big deal. It took about 10 years to get that done. And then a little bit on precip, particularly rain. And then what some of the winter threats are that are around here. So a wide variety of threats. I don't do tropical. I'm not a tropical meteorologist, and so I avoid talking about tropical stuff if at all possible. And so we'll avoid that. But we'll start with looking at in particular, one of my favorite things to talk about, tornadoes. And this is a map showing essentially any tornado, so F0 and higher tornado, how many tornado days per year there are. And essentially, in this part of the world, we run in Oklahoma a little bit over 1 day per year. You'll have a tornado, and this is defined as a tornado touching down within 25 miles of the location. So close enough that you probably are thinking about doing something about it. If you live in the Oklahoma City metropolitan area, that'd be sort of the thing that happens. It's touching down within the metropolitan area. We average about 1 a year for that. Now, there's a fairly large area in the middle of the country where that's sort of half a day per year, so once every other year one comes close enough to think about it. If we restrict ourselves to F2 and greater tornadoes, so the kinds of things that can start to cause serious damage, the pattern shifts a little bit, but it's still kind of mostly the center part of the country between the mountains. And around here again, we come up with having it's about one day every 2 to 3 years. We'll have an F2 and greater tornado touchdown within 25 miles. We see a little bit of an extension of that now off to the southeastern United States, into Mississippi and Alabama, where essentially the springtime issues start to, or the late winter, early springtime issues start to pick up. But again, a fairly broad area where it's the kind of thing you're going to have to deal with on a relatively regular basis. For hail, we hear people use unfortunate phrase, Tornado Alley, which is not a well-defined phrase. So if you ask me where it is, I will refuse to answer it in any sense. But really what we specialize around here is hail. This is any hail, and basically, so that's, again, this is back to severe hail. So it used to be 3/4 inch, and it magically jumped to 1 inch a few years ago. And that's, you know, it's whatever, 9 or 10 days a year we'll have hail within 25 miles. And as far as I can tell, you know, you got to get a little more, unless you've got a really aggressive roofing company coming and looking at your roof, you need to get, you know, more like 1.5 to 2 inches to really start causing real damage to you. And we'll get to that here. Here's 2-inch hail. That's basically, you know, a day every you know, it's 10 days a century, so one day every 10 years we'll have 2-inch hail happen here, and that's as I like to put it, that's hail you can feel. You know, that's when you start to see dents in your car, and you start to have real issues happening. And this is one of the things that characterizes the plains of the United States, probably more than any place else other than the area east of the Andes in South America. We get hail, and we get big hail. You know, if you've ever seen baseballs and softballs fall, you know, if you've seen softballs fall up close, you know, that's kind of an interesting thing. And baseball, okay, here's a little bit of trivia for hail that you want to know. Baseball-sized hail falls at about 100 miles an hour. So if you missed your chance in the major leagues, there you go. Now, and this looks a little bit like some of the tornado stuff. It's concentrated, you know, in the plains as the primary threat. When we look at damaging winds, so this is 50 knot winds, 58 mile an hour winds and greater, we start to see a different pattern. Essentially, east of the Rockies, everywhere. This is based off a 30-year period. We get, again, about the same maximum number as for hail, maybe 10 days a year. Around here, it's only about 6 or 7. One of the things this tells us is the kind of storms that can make high winds and the kind of storms that can make hail are different physical beasts. Hail and tornadoes probably come out of a similar kind of a storm, just without even just looking where they occur. But if we restrict ourselves to the really strong winds, so this is now 75 mile an hour winds, so hurricane force winds, and that's my one mention for tropical, we start to see that comes back to being concentrated in the plains again. So there's lots of stuff that can make 50 knot winds. That's relatively easy for the atmosphere to do. It gets to be a lot harder when we start looking at really, really high-end winds, and they tend to be concentrated into the plains again. So we get some idea that the really strong events probably come out of a similar kind of storm structure. So when do the things occur? The maximum tornado probability, it's a relatively easy map, and if I could show you the same map for hail, and it would look almost the same. If we go to the southeastern United States, we get winds into the you know, the peak timing is into sort of the April-ish, early May maybe, and the timing of the maximum progresses to the west, and then progresses north as we go through the spring into the late springtime. There's some goofy spots down in the southeast where it actually shows up in the fall, and we'll talk about that again in just a minute. And in fact, I want to look then at annual cycles of tornadoes to give you an idea. One of the things again that makes the plains where we are a relatively special place. We can actually make maps of showing the entire, we can do a national estimate of the probability on any given day of a tornado, looking at long time periods. So I've created some smooth fields, did this about 10, 15 years ago. And I'm going to look at different time periods, and we're going to focus only on F1 or EF1 and greater tornadoes, so eliminate the weakest tornadoes. And the reason for that becomes pretty clear if you look at the annual tornado reports. This is the number of tornadoes, exactly F0 tornadoes in the database. And it increases slowly over time. There's a big jump in the early 1990s, probably associated with radar and an increased emphasis on data collection. If I now look at the F1 and graders, we see that that stays relatively constant through time. It's about 500. There's a lot of variability. We have some years that are close to that are around 900 of them back in 2011. Other years that are fewer than 400, such as 2012. And so that's a relatively consistent thing. The F1 and graders don't seem to have changed much if we look at long-term means. But when do they occur? This is now looking at here, Oklahoma City. And this is the annual cycle of tornado occurrence in Oklahoma City, the probability on any particular day. And what you see is there's a very strong peak in the spring. Not much happens after that. Our big threat is, from sort of the middle of March to the middle of June, and after that, tornado threat's really small in this part of the world. And we get up to maybe 1% to 1.5%, depending on what time period we look at. The individual colored lines are different decades, and then the black line's a 60-year record. Now, if we contrast that, we go into southeast Mississippi, we see a completely different pattern. The total overall threat in Hattiesburg is only, in terms of number of tornadoes, is only about 20% less than in Oklahoma City. But obviously, there's just no strong annual cycle. You know, the only time there's not a tornado threat is in the middle of summer, and that depends if there's a tropical cyclone in the Gulf of Mexico. But some of the decades, the peak threat's in the spring. Some of the decades, the peak threat's in the fall. And so they have a very different kind of response and problem than we have here. Here, we need to get public attention for, you know, a brief period of time. There, they kind of have to have attention available all the time for everyone all the time. So if we look at things, we try to look at the long historic record, we focus on those F1 and graders, we can ask some questions about what might have changed over the years in tornadoes in terms of tornado reports. Average tornadoes really don't appear to have changed very much, but when we look at some details, we can see some changes. This is coming out in a paper that I'm hopefully doing page proofs today on. If we look back, the black line is the number of days per year with at least one tornado somewhere in the United States, one F1 tornado or greater. And back in the early 1970s, that number was around 150. That's dropped to about 100 days per year with at least one tornado in the U.S. The red line now, though, is actually the number of days per year with at least 30 F1 tornadoes. That used to be average about half a day per year, so one day every other year in the 1960s and 70s. We now average around 3 days per year. But we end up with the same total number of tornadoes during the year. We have about 500 tornadoes, but we have 1/3 fewer days per year with tornadoes, but 5 times as many days with at least 30. So in effect, we've concentrated the number of tornadoes in the U.S. into a smaller and smaller number of days. And I'm not completely sure of what all the implications for users are of becoming a more, for lack of a better word, outbreaky with tornadoes than we used to be. But there are some things that happen in terms of resource management when you have to be prepared for a big event and not as many small events. We can also look at when the season starts. Like I said, there's about 500 F1 tornadoes a year, F1 and greater tornadoes a year. So I've arbitrarily picked the date of that the 50th tornado during the year occurs. And what we find is it averages about March the 22nd. And it's been like that for if we take the average. But if you look at the last 15 to 20 years, we've had 4 out of the 5 earliest starts to the year and 4 out of the 5 latest starts to the year have all occurred in the last 15 years. We're seeing a much wider and a much greater variability in the timing of occurrence of tornadoes. We get some years that we start off very fast, and we get some years where we just have nothing happening at all for a long time. We don't have a good physical model for why this is occurring yet, but it's certainly an interesting model. And this is dominated by the southeastern U.S. The plains don't get involved in tornadoes until a little bit later. And so in general, we're seeing a much greater variability in tornado occurrence. If we look in just the plains, there was a paper that got published last week that actually looks at the annual cycle of tornado occurrence in the plains. They've done some this sort of elliptical shape is essentially an effort to do a circular density of when tornadoes occur, and the arrow points to the maximum timing. And if we look in the early part of the record, the 50s and the 60s, the average maximum the timing of the maximum was May the 25th. And that's actually now moved 11 days earlier than it was, without changing the total number of the total threat. The total number of tornadoes in the different decades is about the same, the way they've treated the data, but tornado season appears in the plains to be shifting a little earlier, by about 10 days over a 60-year period. What impact that has on you, as you as an individual, that's not completely clear because the number of threat is the same. The interesting, really, implication is that we have certain assets, such as schools, that as we move, if the tornado season moves earlier, we start having a greater part of it during the school year than it would have been in the past. What impact that has is really not clear yet. This is like I said, this was published last week, so we're still trying to figure out what it means and going on. Well, so that's sort of a big end threat, tornado, or sort of dramatic threat. We heard a lot about rain a few minutes ago. And we're going to look at where rain occurs in the U.S. And this is looking at 1 inch per hour. This is over, I think, a 30-year period we did an analysis of. 1 inch per hour rain rates for each month. And so the dark colors have a lot more days per month. So that, for instance, if we look in June in Kansas and Nebraska, there's a little over 1 day or 1 day every year that they get at least 1 inch per hour. And 1 inch per hour rain, this map would look the same if I did other thresholds, like 4 inches in 3 hours and things like that. That's where you start to actually see flooding, a lot of local flooding problems, because the systems don't handle that amount of rain really, really well. But we see sort of how it moves around. It starts off again, just like the tornado threat in the southeast in the springtime, moves into the plains and kind of gets stuck in the plains in the late spring. And a lot of that occurs overnight, actually. And then there's this very large diffuse mass of very heavy precip over much of the country, and then it dies away and continues sort of into if we go from, say, eastern Oklahoma into Mississippi, then in the fall season. And so there's a long season for heavy rain compared to the tornado season over much of the country. And if we actually look and see how much rain is falling on a little bit lower threshold, this is based on 1 inch per day, or 1 day precipitation. Looking at the heaviest I think it's the heaviest 10% of rainfall events. We see that's increased over the last century, where we've almost doubled the number of the amount of rain that takes place that's taking place on days with the heaviest possible rain. And we can actually specifically look at Oklahoma City. This is just for July. And I've plotted up a running 20-year probability of precipitation in the blue. We have it rains about 20% of the days in Oklahoma City. But given that it rains, we've had a very large increase in the probability that we'll get at least 1 inch in a day. Back prior to 1990, that was running about 10%. We now are about 25% of the days that it rains, we get at least 1 inch of rain in Oklahoma City. And again, if I did higher thresholds, you'd see a very similar one. So that we haven't really changed very much the total number of days it rains, or the total amount of rain during the year, but we're now having a lot of days with much lighter rain, and when we do get rain, we get a lot. And it ends up averaging out to being about the total amount. And again, your infrastructure responses, when you start getting inches of rain in 1 day, is a whole lot different than if you get those inches of rain spread over the course of a calendar month. And I think hopefully we're gonna do some analysis here to see how far out this goes in other locations, and just see how it is. We know that nationally, if we take a look at the fraction of the rain that occurs on the 1% heaviest rain days, that's increased dramatically in the eastern 2/3 of the U.S. over the last century. We also have to deal with winter, and we don't do a great job of collecting winter weather obs. We've changed the way we've collected them over the years, and so this is going to be, if Esther's going to work on this problem, it's going to be a really challenging problem in terms of some of the data collection. This was a paper that a postdoc that I worked with did now it's almost 20 years ago, looking at about 40 years of observed data, and looking and seeing, just counting how many hours had various kinds of winter precip. Freezing rain in the upper left-hand corner, freezing drizzle in the upper right, and then ice pellets or sleet in the bottom. And the contours are 10 hours per year. And one of the big things that you notice is that around in our part of the world, we actually average about 25 hours, that's the dashed line, 25 hours a year with freezing drizzle. Freezing drizzle is a real pain in many parts of the body. It's hard to forecast, because you're not talking about large amounts of water falling out of the sky. So that makes it hard to forecast. It's forecasting half an inch of rain, that's okay, but with drizzle we may be looking at a couple of hundredths of an inch. But that's enough to make, depending on where you live, your drive to work incredibly interesting. Now the freezing rain part up here may have more of an impact on sort of utilities, because you start getting lots of ice forming on power lines and on trees and taking that down. Drizzle may in fact be a bigger problem for transportation interests, just because it's such a light glaze, and like I said, the difference between forecasting 0 and forecasting 1/100 of an inch is not that big. But yeah, the impacts can be really huge. And in terms of how this is, if this is changing, how it's changing, this is actually a pretty complicated problem to figure out. So I was asked to talk some about weather forecasting, and I realized I had two choices on how to cover this problem. Okay, and we could vote, but we could. And the first one, let's do a semester-long course or courses. The second is we'll do the 10-minute layman's approach. I've gone with the second one, so those of you who were looking forward to a scintillating discussion of quasi-geostrophic potential vorticity, you're out of luck today. We'll try to come back to that at some other point, perhaps. So if we want to think about, okay, when I think about weather forecasting, I think about, I had the chance to go in 2000 to the first European Conference on Severe Storms in Toulouse, France, with some of my colleagues. And I had a friend who was working on his PhD in medieval French literature at the time. And so he, I said, I'm going to go, hey, what should I be looking forward to eat while I'm there, being something that's what I really care about when I go to conferences. And he just comes up and he says, I have one word for you, cassoulet. And I go, oh, okay, yeah, we'll watch for that, whatever it is. And we get to check into the hotel, and the hotel says, you're looking for a recommendation for a restaurant. And he goes, go to this place, tell them we sent you. We go, oh, all right. We go in there, and we get this waiter who is rather outgoing, and he says, is this your first time in Toulouse? And we go, yes. He goes, then you must try our cassoulet. And the three of us go, this is what we're supposed to be looking for. And it was really wonderful. It's a bean stew. It used to be a peasant thing, bean stew with some protein of some kind in it. And in Toulouse, it's duck and goose. Well, and so one of the things that we think about that this is going to relate to weather forecasting in a way that you may not understand, is that, there were the three of us at the table were thinking, we wouldn't mind having this at home. Okay, we've got a problem. We have to figure out what the ingredients are to make it. And some of them were pretty obvious. We've got beans, we've got something made from a duck and something made from a goose sitting in here, and there's some other stuff. Okay, so we might be able to make a guess at what the ingredients are that we needed to do it. And then we needed to figure out the process to bring those ingredients together in the right way. And that's essentially what weather forecasting is trying to figure out what the ingredients are and what the processes are that bring them together in the right way. If we were wrong on the ingredients, we might get food, but it wouldn't be cassoulet. And if we had the processes wrong, it would be food still potentially, maybe for the dog, but it wouldn't be cassoulet like we had in France. And so now, if I was an expert chef and had been trained, I probably could have picked up on a lot more of the flavors of the spices and all that. I could have made it more accurate. And so that's what hopefully meteorologists learn to do, is they learn more of those details so they can pick up what those ingredients are. So our challenge in weather forecasting is understanding what are the ingredients you need to make a kind of weather event that's of interest. And if they aren't present at that time, what are the processes that will bring them together to actually make that happen? And we start by looking at what's going on now. Where are the ingredients that we might need for something? And then what will bring them together if they're missing? And to know that, we do a whole bunch of things. We have to have some kind of theory of how the air moves, physical understanding of how whatever thing we care about works. Like I mentioned, freezing rain and freezing drizzle formed by completely different physical processes. They're different things, completely and totally. Freezing drizzle, this may surprise you, forms by something that in meteorology is referred to as the warm rain process. It will not make really big raindrops, it makes very small drops. So what happens physically to create it is different than what happens with rain. And we use lots of computer models that will help bring those in, that will help us bring those in, that will tell us how the air is going to move to bring the ingredients together. I'll focus a little bit on the ingredients for my favorite thing, severe thunderstorms, and in particular something called the supercell. If you live in the Oklahoma City area, you live in the only television market that will use the word supercell on TV, and usually use it correctly. That's an important point. To make a thunderstorm, we need lots of warm, moist air at the low levels of the atmosphere. We need to have relatively cold, dry air in the mid levels of the atmosphere. And we have to have something to lift the warm moisture up, a front or a dry line or something like that. And we can do some things to get the first two, the thermodynamics, get to be energy. And then we need to organize the storm so that it will rotate. And to have that, we have the winds that increase and change direction with height from the over the lowest few kilometers of the atmosphere. And typically, they blow from the equator at the surface and from the west to loft. And one of the things that makes this part of the planet absolutely unique is that if you look at a map, when we look at when the winds are blowing out of the south, in the south-central U.S., it's coming off of the Gulf of Mexico, bringing up the warm, moist air at low levels. And if you want to get cold, dry air aloft, you bring it over a wide, high range of mountains. And the Rocky Mountains are there. It's very difficult to get the air overhead here that hasn't been over the Rockies or the high desert southwest. No place else on the planet brings those two things together. That's why we get so many severe thunderstorms and why we get so much hail and tornadoes in the central part of the United States. Particularly for practitioners, some resources hopefully you can use. The Storm Prediction Center, which is located directly through the ceiling. If the engineers were wrong and something collapses, the Storm Prediction Center will be in our midst. They put out forecasts on a daily basis of severe thunderstorm threats, and this is their convective outlook actually from this morning. So possibility of severe storms up in the upper left, and then we got separate forecasts for tornado, wind and hail down in here. So if you want to see severe thunderstorms, get yourself to South Dakota very, very quickly, and that'll be your best bet at it for today. They also put forecasts out to 8 days in advance. And for instance, the threat for Thursday, for Thursday, this is there's a slight risk of severe thunderstorms covering eastern Oklahoma, Arkansas, and Missouri. This is available on a daily basis. I don't think the convective outlooks are used as much as they should be by people. After they put this out, they'll put out severe thunderstorm and tornado watches as necessary. But this is a pretty good way of looking at how we do things. For heavy precip and for winter threats, there's the Weather Prediction Center. Don't ask how these things got named. That's not fair. This is, again, today's forecast, a 24-hour forecast ending tomorrow morning. And the probability of heaviest rain is up sort of in the Omaha area, and they're forecasting an area that'll get at least an inch of rain. This isn't the most interesting rainfall forecast they make. And then for everybody, wherever you are, there's a local forecast office. This is the Norman page. And you actually see that this is actually from their front page of their website, this is actually looking at what, Tuesday night and Wednesday, or Wednesday night and Thursday, the probability of rain, with a little bit of layman's discussion. Now they have on that page, they have much more technical discussions available to you that will go into physical processes and what they're thinking and what the limitations are, what they know about. But they do a very good job in most of the forecast offices now giving you an idea of what's going on. I want to look at a couple of events from this last year to sort of highlight some things. One of them, there was actually a picture from one of these out on the Weather Channel while we were out there. Some tornadoes that occurred in the south-central U.S. And this will give you an idea of some of the challenges we face in what we do with forecasting. This is from the April 27th and 28th. There was a series of 4 days with interesting weather. There were a few tornadoes on the 27th up in north-central U.S. And then the big day. The two big days were the 28th and the 29th. The 28th, you may remember the tornado of Bologna, Arkansas, that resulted in a number of fatalities, closed the interstate, closed I-40 because of debris across the highway. That was on the 28th, and then the 29th, more tornadoes that came in through the 27th also included a tornado in Mississippi, Louisville, Mississippi. Which are also fatalities, and then more tornadoes in the east coast. And then as the system moved east, the front associated with it stalled, and there was on the order of 20 inches of rain in Pensacola, Florida. And all we could see if you were a forecaster is slight differences in the ingredients that are present, and in many ways what appear to be very subtle differences going on that lead to radically different weather. The precip event wasn't a big deal on the first 3 days. Tornadoes weren't a big deal on the 4th day of the event, but they combined to be big threats of different kinds all the way through. And this was actually all of the watches that were issued and the warnings that were issued by the Weather Service, just to show that they did a good job. We can produce maps that help put these ingredients together. The arrows are winds at different heights. The red is at low levels, and the blue is higher levels, and you see that change of the wind with height that I mentioned over an increase in the wind speeds from 40 knots to about 70 knots, centered over into Arkansas. And as storms are starting to form, you can see the satellite image of the first storms forming. This is where the big problem was for the tornadoes on that day. And we go on a little bit later on, and now the wind, the next morning, that has shifted a little bit further east, and now the threat area is over Mississippi, and this is now the Louisville or Louisville tornado sounding, and we got damage that out of the Mississippi events. Well, the upper left-hand corner is Bologna, and you can see the track from satellite going right across the highway and up through Bologna, and then damage on the ground in the Mississippi tornadoes, and that's some before and after shot of the damage. This was we had a total of 70 tornadoes, 34 fatalities. It's the second time that Bologna has been hit hard in the last few years, and the fifth in 60, 70 years. It's the third largest outbreak in Mississippi on record on that one day. Half $500 million in property damage almost. And so we had the ingredients we could see coming together. And then as that front moved on, as the front moved and it started to stall, we get now those storms. So this is essentially a continuation of the storms that we saw that I showed the brief satellite image of. And the front is on the red, is the red line going through there. As it stalls, essentially the storms move now along the front, and we no longer have that change of the winds with height that we had before. There's essentially all the winds are aligned with the front aloft, and so new thunderstorms form and continually move along into the exact same place. And nice satellite image of what's going on at the height of the storm. Lots of what we call precipitable water, so lots of moist air coming in, much moister than ordinary. And this is an estimated rainfall map out of everything we know. The white is basically what the height. White's 10 inches, no 12, 15 inches. 15 inches of rain over that large of an area. Over in a period. And 100 to 200 year of rainfall event in the Florida Panhandle, they get hit by a lot of tropical cyclones. They get 20 to 30 inches of rain. That's a big deal. We had these are pictures out of Pensacola. We've lost part of a road there for you, so we can have that. And part of another road up there. There was an explosion in the jail. Apparently they tried to get ready to protect some assets from natural gas, and somebody didn't turn something off correctly. And so when the waters came in and flooded, they had boilers blowing up in the basement of the jail, which isn't real good. They had almost 6 inches of rain in 1 hour. That will change your world. 16 of the inches fell in 24 hours. It broke a record that was set in 1879. Lots of places with a foot of rain, and sort of really huge long things. So heavy rain, it destroyed a lot of infrastructure. One of the big things about rain events sometimes is that tornadoes put debris across roads, can cause problems. But as we saw earlier, you get a lot of rain and your road disappears. And so even just the act of getting assets in to take care of the problem becomes a real issue when you lose the road. I'll suggest to you, if you ever go towards Rocky Mountain National Park, driving up the Big Thompson Canyon and thinking about what's happened there twice in the last 40 years is a pretty dramatic thing. And looking at some pictures of the road essentially completely disappeared for about a mile-long stretch in 1976. And they had to helicopter in to get everybody out of the canyon when that happened. Okay, I'm gonna finish with a little bit of ice. I'm not a winter weather person. I don't like winter weather on a personal and professional level. This is a temperature and moisture profile. I should have moved it up a little bit higher for display. This horizontal line, not horizontal, this slanted line is the freezing line, freezing temperature. And what we typically see with freezing rain events is the temperature at the surface is just below freezing, and there's this large area, a couple of kilometers deep, of temperatures that are well above freezing. So the precip starts off as snow, it melts as it goes through that really warm area, and then just as it gets to the ground, it freezes. If this warm area was a little bit deeper, you'd get ice pellets, you'd get sleet, it'd have time to completely freeze instead of waiting until it gets down to the ground. As I mentioned, freezing drizzle looks very different than that. This is a winter map from a few years ago, and I'm going to skip right over to this one. What we ended up having in this case, this was over, the main threat was over Kansas and Nebraska, was an inch of precipitable water, which is a lot of water. Essentially, you could think of, we could probably milk that out of the atmosphere and produce up to a couple of inches of rain if it was continually getting pulled in. Going over a really cold air mass as this cold front came south into the central part of the U.S. And so we put a heck of a lot of water over very cold temperatures. And when it all falls out, we get ice covering everything in the state of Kansas and half of Nebraska. And it was coming in the winds were blowing at 40 knots aloft, and so this was bringing it up very quickly, replenishing it. And so if you've ever been in a really big ice storm, just move the map around to different parts of the country. This is exactly what's happening almost all the time. And we're pretty good at forecasting really big ice events now. That's something that we start to understand pretty well, and the large-scale processes have to be going on. As that moved down 2 weeks later, in fact, to show you an example, this is 2 weeks later. Virtually the exact same situation, except the cold front's further south, and we now have over eastern Oklahoma up through Illinois. Again, lots of water coming up over really cold air. The worst part of the storm, we got ice here, if I remember right, a little bit. But the worst part of the storm was over essentially over I-44 going through Missouri, and they had a very long area of 1 to 2 inches of ice that came out of that storm, and that's 50 miles long, right up the axis of the highway, with 1 to 2 inches. That will, I believe, change your view of the world, and that's the really pretty pictures that they got after it. If you've ever been inside of an ice storm, one of the really spooky things I learned was listening to the big trees crack. That's one of the scariest things in the world. The power's out, and so it's completely silent, and all you can hear is I'm not real thrilled with that. And so the first one closed I-70 all through Kansas. The second one pretty much closed I-44 through Missouri, and there ended up being 87 deaths associated with it, and it was just powers out from Texas all the way up to New York and in some places. So to close, we got a wide range of hazards. Essentially, virtually everything that can possibly happen weather-wise happens somewhere in the south central U.S. At some time during the year. We tend not to be real big on like permafrost, but other than that, we get everything. And one of the big issues is we could have multiple threats in a very short period of time. Actually, if you line things up exactly right, we can go from having severe thunderstorms to having freezing rain within the course of about 36 hours. And then trying to clean up from the tornado is really bad when there's ice all over everything. And that happens sometimes. Our limits to what we can do with forecasting these things, we're much better than we used to be. Dave Parsons talked a little bit about that earlier. We don't observe everything we want to know. We don't observe things above the ground as well as we observe things at the ground. And lots of the things we care about actually take place weather up there above. Our physical understanding of events isn't perfect. There are things that can happen, especially with heavy rain. Heavy rain can happen in a lot of different ways, just like wind can happen in a lot of different ways. Our physical understanding of everything isn't as good as we'd like it to be. And it's hard to model some of these things because we care about really small things. If you think about what happens to make rain and freezing rain, we actually care about what's happening essentially on the molecular scale. How do the raindrops grow? They grab more molecules of water and add them up. Well, that happens a lot smaller scale than anything we can possibly model. So we have to, what we do call parameterizations and make estimates of what we think the bulk effects are of things. And that is always a limit to what we can understand. But hopefully we can provide you guys with some information that can help you make your daily lives a little bit easier. I'll take some questions now. Got a couple minutes.
I'm going to ask a question.
Yeah.
So the graph you showed with the number of days with greater rainfall, red dots, since 1990 really increasing quite steeply, to me that's of particular interest because I study soils and response of soils to wetting and drying cycles. And drying cycles can be very bad because when we deal with clays, they shrink and crack, and then wetting cycles can be equally bad because those dry clays then imbibe water and can lead to slope failures, and if they're expansive, it creates problems. So I'm real interested in that trend for that reason. It seems that slope is still going up, and I'm wondering, there must be a limit to that. So I guess
eventually there's a limit, yeah. One of the things that the climate models are pretty consistent about is the notion that, even without a really large change in the overall precip during the year, this notion of concentrating the precip on a smaller number of days and having either fewer days with rain or more days with very light rain, and then a small number of days with a lot of rain, that's pretty consistent. And that's what it looks like we're seeing in the Oklahoma City area, in the observed record, and we see it in other places too. And it's a real tough problem, because it is. I mean, it's a things dry out so fast. I mean, just looking at my lawn, things dry out really fast, and then you go, well, then let's put an inch and a half of water onto it, and and just watch it run off and it's wet for a few days, and then it dries out again really rapidly. I think that's one of our big challenges in the future is if.
So do you think that trend will stay?
I don't think it'll stay forever, because there's enough water to, because the limit of it would say we get all the rain in the year in one day, which is not going to happen. I don't know what the upper limit on it is.
Do they know? Is there any? Do they have? Does the climate scientists have any idea why that is the trend right now?
Well, essentially, it's a in some sense the hydrologic cycle is intensifying. If you think about to make rain, we need to bring in water vapor from an area around it. It appears that things are. We know that there's more water vapor in the atmosphere, because of as the temperatures warm, the amount of water vapor also increases with it. And so essentially we're processing that water more rapidly. And when you lift the water up, that stabilizes the atmosphere, so you don't get anything for a while, and then eventually we pull more water in. And it's a relatively consistent proposition that's going to be happening in a lot of places.
Interesting. Any other questions for Dr. Brooks? I see two hands. We'll go with Dr. Zaman. I think he was quicker.
So one question I have in terms of modeling challenges, we have a lot of development in recent years in terms of power and so on, so you can do really a lot more. But what are if we had to pick one or two challenges, what those challenges would be?
Number one is, and probably number two and number three and number four, have to do with these things that it still happens inside of the scale of what we actually model on our grids. When we worry about things that happen right at the ground and the boundary layer of the atmosphere, and what happens between the soil-air interface. We're never going to be able to model that at the molecular scale, but that's actually where the process takes place. And so we have to do a better job of understanding that. The second thing is that we will never have perfect models. And so how do we deal with the fact that the models are imperfect in terms of, say, using ensembles of models and coming up with reliable probability densities functions for the forecast? That's a really hard problem, because we know that the models aren't perfect, but they're still useful. And how do we maximize the use we get out of them?
One quick one, Dr. Morelli, and then we'll.
So you listed three things which are needed for better forecasting. If you had to pick one to improve to get a better forecasting, which one of those would that be?
Because of my background, I'm duty bound to say physical understanding. I think that comes back to how do we model these kinds of processes we can't see very well. Some of them we can do. We've made vast improvements over the years in things like how do we model the impacts of thunderstorms on scales that are smaller than what we actually do. Some of the other ones, like the what we call the boundary layer of the atmosphere, some of the energy transfers within the lowest kilometer. There really hasn't been a major new breakthrough in that in a couple of decades. But we know it's really important. And then what happens with friction at the ground? I was a physicist undergraduate, and so I was taught to ignore friction most of the time. But we know it's important.
Great. Well, thank you very much.